Hi guys, so this is section 9.1, defining the ideal solution. In an ideal gas, which we've talked about quite a bit, one of the properties of an ideal gas is that there are no interparticle interactions. That's impossible in a liquid though, because in a liquid the particles are touching each other all the time, and of course they're going to interact. So we're going to start out with a vapor that's in equilibrium with a solution. And we'll start out with a definition which we'll derive here in a little bit. And that is, an ideal solution is one that obeys Raoult's law. And this in purple here, or blue, whatever, that's Raoult's law. What this says is that the vapor pressure above a solution of component I is equal to the mole fraction of that component, this is a chi, times the vapor pressure of that component when it's pure, when it's by itself. No solute in it, or no other components in the mixture. And so a definition real quick, we call the solvent the species in that solution that has the largest mole fraction, that there's the most of. All other species are solutes. So this is the picture, a good picture to think about when we're talking about this. Here, there's two species in this solution, the white spheres and the dark spheres. There are more white spheres, they have a larger mole fraction, so that would be the solvent. The dark spheres would be the solute. And so the idea is that these particles are evaporating and condensing all the time. So in an ideal solution, that is one that follows Raoult's law, all of the particles interact equally. That means that the solute interparticle interactions have the same strength as the solvent-solvent interactions, and which are the same as the solute-solvent interactions. Down here in red, this is an easy way to think about it. Let's say A is the solvent, B is the solute. So the AA interactions are equal to the BB interactions, or equal to the AB interactions. Now this doesn't happen very often in real life. A good approximation to this would be a toluene benzene solution, because toluene is basically benzene with a methyl group on it, so they have the same polarities, same intermolecular forces. But most solutions don't follow this behavior. However, a real solution, that's a solution that's not ideal, like a real gas, as opposed to an ideal gas. The behavior of a real solution approaches that of an ideal solution. Its limiting behavior is that of an ideal solution, following Raoult's law, as the system becomes very dilute. More and more dilute it becomes, the closer its behavior becomes to ideal. So now we're going to do a little derivation of Raoult's law. So we're going to assume that the rate of evaporation and rate of condensation of the solvent at the surface of a pure liquid, or the pure solvent, before we add the solute in there, are given by the rate of evaporation. So R evap is the rate of evaporation, is equal to A, which is the surface area of that liquid, times the rate constant for the evaporation. So this is basically first order kinetics, right? Which makes sense because there's only one species involved. And the rate of condensation also makes sense to be proportional to the surface area. The larger the surface area, the more molecules will evaporate, times the rate constant for condensation, times the vapor pressure of the pure solvent. So this asterisk is going to mean pure substance, pure liquid. So at equilibrium, the rate of evaporation is equal to the rate of condensation. So we set these equal to each other. Rate of evaporation equals rate of condensation down here. So that means we get this equation right here. If we rearrange this, solve for the vapor pressure of the pure solvent, P star solvent, the surface area cancels, and we just get that the vapor pressure of the pure solvent is equal to the rate constant for evaporation divided by the rate constant for condensation. So that makes sense, right? Because the greater the rate constant, if the rate constant for evaporation is greater than the rate constant for the condensation, then we're going to have a large vapor pressure and vice versa. Now, let's throw a solute in there, an ideal solution. And again, remember, this is where all the interparticle interactions are of the same strength. However, because now we have solute particles in there, they're going to reduce the surface area where the solvent molecules can evaporate. We're not going to worry about the solute particles evaporating now. At this point, we're going to assume that the solute is non-volatile. So there are fewer molecules of the solvent at the surface area, so its rate of evaporation is going to be decreased, and that's going to be proportional to the mole fraction of the solvent. The greater the mole fraction of the solvent, the greater the rate of evaporation, right? And vice versa. The smaller the mole fraction, the smaller the rate of evaporation. So now we would write the rate of evaporation of the solvent is equal to the mole fraction of the solvent times the surface area times the rate constant for evaporation, and the rate of condensation is still the surface area times the rate constant for condensation times the pressure of the solvent, which is not the pure solvent anymore. So notice we don't have that asterisk anymore. Of course, we don't write the mole fraction over here because this is in the gas phase, right? And so it's at this point there's just the solvent molecules up there. The mole fraction's not going to affect it. But same thing, at equilibrium, rate of evaporation is equal to rate of condensation. So plugging these in, get the mole fraction of the solvent times the surface area times the rate constant of evaporation is equal to A, K condensation, pressure of the solvent. Solving this equation for the pressure of the solvent in this solution, okay, the A's cancel again. We get the pressure of the solvent, this right here, is equal to the mole fraction of the solvent times the rate of evaporation, the rate constant for evaporation, divided by the rate constant for condensation. But we just showed on the previous slide that this ratio is equal to the vapor pressure of the pure solvent. And so we get Raoult's law. Vapor pressure of the solvent in an ideal solution is equal to the mole fraction of that solvent times the vapor pressure of the pure solvent.